in the start of the recording, what I'm trying to highlight here is that at the end of the sequence of slides, we do get a bunch of repeat slides. So starting about slide 83, okay, 83 to 82-ish are super important slides because they're review slides for substitution and elimination. So you get the basics of the substitution mechanism. Then you get a substitution summary for SN1. What would you expect? Substrate, leaving group, nucleophile, solvent, complications or benefits depending on how I pitched it or wrote it at that time. And then you see it for SN2, same deal. Whoop, all of that breakdown. Then it's summarized into one slide where it shows all of those pieces. And then you get elimination, same deal for E1 and for E2. And the E1, E2 split. And then what Carty goes through and does is this kind of neat table. While I like, the idea of that table, I don't agree with his categories. So I created this one, which does effectively the same thing. Okay? So what you would go through and do for each of those factors, decide which mechanism does it favor, okay? Or which mechanism allows it to happen. And what you could then do is just total it up for each of those columns. Whichever one has the most factors that supports it, it's likely that mechanism. Okay? So it's a neat little idea that he came up with and put in his book, so I just switched it to match my things. Then looking at some kind of big questions, if you're trying to decide between substitution and elimination, kind of the bigger questions that could help you differentiate which mechanism you're looking at or which reaction you're looking at. And that's the last of the slides. Okay, so that is literally slide 83 to 92, and this one's 92. Okay, so these are all the big picture ideas. So if you're going through and trying to do the homework, and by if, you should be going through and trying to do the homework, you can use those last roughly 10 slides to help kind of act as a cheat sheet to get through them. Okay, it summarizes the big concepts with minimal explanation so that hopefully you'd be able to figure it out if you had a brief skim through of the textbook kind of stuff. Make sense? Okay. With that, I'm going to pause the recording. On Wednesday, was looking at this slide with all the thermodynamics and Gibbs free energies and fun stuff on there. It's not that we're entirely ignoring this, but I'm kind of saying that you picked that up in 152 and I don't really want to talk about it again. Okay? It is important, but really what it's important in referencing is looking at the basics of energy diagrams. And this is ultimately what you did in 152. Right? Depending on your 152 class, you may have done it in slightly different orders, okay? But at least when I taught it, the general trend was to talk about kinetics first, right? And kinetics was looking at how long your reaction happens. So looking at the activation barrier, so between the reactant and the transition state. Okay? So you looked at all those different things. In those, you looked at mechanistic steps. Okay? Chapter 7 in our textbook is those mechanistic steps. Okay? So what we'd be doing is evaluating how a reaction happens by looking at each of those steps. The second part of second semester Gen Chem was thermodynamics, and that was looking in this bottom section, reactants to products. Okay? The whole point of 152 is ultimately to get you this energy diagram, because this energy diagram we could now use to help predict different reactions, right? And describe how they function, particularly if we quantify the crap out of it. We aren't going to quantify it. All we're going to do is use general trends to help us kind of bit and process our way through it to look at differentials or where things pop up that could be problematic. Okay? Which gets us into strengths of charged and uncharged acids. This is kind of something we already addressed. If we go through to look at this particular reaction, we're mixing water with water to produce H3O plus and hydroxide. Okay? So we're looking at how water reacts with itself. We can look at KEQs, we can look at delta Gs and all sorts of fun stuff. Okay? But ultimately, really what we're zeroing in on is the stronger the acidity, However, a positively charged acid is a reflection of the lower stability of the charged species and similar to uncharged. Okay, so it's just saying charged, more unstable than uncharged. That's it. That's all we want. Okay? Which kind of makes sense because it's how we've addressed virtually everything. Okay? All the way back to atomic structure. Okay, we have a proton. What needs to be with a proton? And an electron to balance out the charge. That's how we get atomic structure. Okay? The same thing's happening now, but at a molecular structure. That imbalance of charge we can use or take advantage of to predict reactivities. If we look at an energy diagram, that's all that's being said here. Okay? Our delta G is referencing that difference in energy. Because the delta G is positive, we know this is an endothermic reaction. Products are higher than reactants. Okay? The transition state, because I don't know if our textbook explicitly mentions it, typically represented as a double dagger. There's something known as the Hammond postulate, okay, which is kind of a simple postulate with a bunch of fancy words that ultimately says the transition state, okay, what the picture of our transition state, what the molecules look like at the transition state appear most like the species they are closest to. So for an endothermic reaction, our transition state looks most like the products, because the products are closer in energy to it. Okay? That relatively simple statement can be used to explain a lot of different reactions and balances in different reactions. Okay? So you may hear reference to it again. I will try to bring it back because I know people like talking about it. Okay? So if we went through to look at these reactions, CH4 versus NH3 plus water. Okay? What do you think we're referencing these acting as? CH4 is going to act as an acid? Yeah, let's have it act as an acid. Okay? If we're going to have the CH4 act as an acid, we'll also make the NH3. See, I was being nice because I could have asked you NH3. CH4 is a straightforward one. Why? To act as a base, what must it have? Donatable electrons to act as a base. Does it have any electrons to donate? No. If it can't act as a base, it should act as an acid. Why is NH3 more difficult? There's an implied lone pair on that nitrogen. That implied lone pair means that that nitrogen could theoretically act as both. Okay? So in this case, we're going to have them both act as acids. The CH4 donates a hydrogen. We'd end up with
CH3 minus.
With a lone pair, negative, and H3O plus. What happens if we go through and look at the ammonia, or NH3? What do we get?
NH2 minus.
NH2, two lone pairs, negative charge, plus our H3O plus. Which of these reactions is more likely to occur? NH3 to NH2 is more likely to occur. Why?
Because it is a more electronegative element, and so it's more comfortable stability.
We're referencing these acting as acids, so we look at the stability of our conjugate base. The first thing we would evaluate, it's charge. They're both charged. There's no difference, so I can't use charge. The next thing I move to is size. Is there a difference in size? Nope, so I move to electronegativity. And as David was suggesting, the nitrogen being more electronegative is doing what to that charge? Holding it tighter. If it holds them tighter, they're less reactive, making it more stable. How does that translate into an energy diagram? Okay, well, both of these are starting relative or neutral, so relatively the same energy. So here's our reactants, both in the same spot. Would we expect the products to be higher or lower in energy? Why should they be higher in energy?
Because they are charged.
They are charged. Okay, so let's go ahead and draw in the blue one. There's the blue one. It is higher in energy. So I could look at my energy diagram. Ta-da! Is that all we really need? Yes, that's all we're looking for. Okay, what about the nitrogen? Is that nitrogen higher or lower in energy than that carbon? It is lower in energy, which means I draw that well below it. Now what happens? Kind of squished there. Which of those reactions is more likely to occur? The red one. Why?
Because the final product is lower energy.
So we could do a final product analysis. Okay, that final product is lower in energy. What else could we use?
The activation energy.
The activation energy. We go through and look at that. The activation barrier for the nitrogen is a little bit less than for the carbon. Why? It's closer in energy to the product, right? Because the product is lower in energy. What does that do to the activation barrier? That also drops it a little bit. Okay? That exact effect can be very subtle and it can be very extreme. Okay? What we want to get out of this is just the ballpark figure of roughly what's going on here. That's all I want out of this. We can get a whole lot more detailed, okay, and referencing how the textbooks got this up. And you can still see those differences. And actually, I thought they even did a little bit more than that, but they didn't. Okay? The exact values the textbook has put for where those things are, they didn't specify any of the numbers, but I'm going to bet they used the numbers to come up with this diagram. Okay? 152 does a great job of looking at the numbers. And if you want to deal with numbers, that's fantastic. Go back to 152. Okay? If you don't want to deal with the numbers, what you need to be getting an idea of is how we evaluate those 5 rules. What were those 5 rules? Charge, size, electronegativity, resonance, and induction. Okay? By using those, we can predict something about our energy diagram and thereby predict something about the likelihood of the reaction happening. That's what we want. Okay? Ion stabilities. Okay, so in this case, if I was to decide which of those was more stable, which one is it? Okay, the top one. Why is the top one most stable?
Because the bottom is least stable because it has more electrons.
Okay, so you're saying the top one is most stable only because the tertiary is less stable. Why is the tertiary less stable?
It has more electrons than it can take.
Okay, it has more electrons that it can take. I don't quite understand that. I know where you're going.
Zero-ary is, there's not as large an electron cloud around it. So the hydrogens don't have as many, they don't contain as many electrons, so there's not as many things interfering with it.
So the very first question we should ask, what makes all of them unstable? The negative charge. What is going to make that negative charge more stable? More positive charge near it. But we don't really have any positive charge that we can reference here. And in fact, when we think about organic chemistry, do we move positive charge? No, we move electrons. So these are all unstable because they have too many electrons. Okay? So what could we do? We could try and make sure that those electrons get shared with something else, but then all of those have an equal probability of sharing. So that doesn't quite work.
There's more space for the electrons.
What is the difference internally for each of these? Each of them all has 3 bonds. That's not a difference. The bottom one has carbons instead of hydrogens. Well, now what's the difference between carbon and hydrogen?
Not a lot, but there's a difference.
Okay. We could evaluate, I don't know, say charge. Oh, there's no difference. We could evaluate size. Is there a difference between size between carbon and hydrogen?
Yes.
Yes. Why?
Because hydrogen have a 2 orbital, a 2 energy shell.
Let's
Because
back down the
it's
science. We don't need to go that far.
Hydrogen has less electrons. It's removed.
I could stick with that. Hydrogen has less electrons than carbon. Carbon has more electrons. Okay? There's our size argument. Carbon has more electrons. If I put more electrons near a negative, is that good or bad? That's bad. I'm putting too much charge in the same spot. That makes it more reactive. Whereas in the top case, I'm not adding that extra nastiness. I'm not helping it either, but I'm not adding more charge to mess with it. Okay? That makes the top one more stable than the bottom one. Okay? Are we still using the same rules that we've been using? Charge, size, electronegativity? Yeah. It's the exact same system. Okay? It's just a question of how and when we decide to look at it. Okay? We saw this in reference back to our carbocations and ultimately our radicals. It's the same concept. It's just a different spin on the same topic. Okay? So when we look at our stabilities, okay, of those individual atoms, of where those charges are held, sometimes we'll have to get into looking at something like this. Okay? I would argue this stability difference between that zeroary versus the tertiary, okay, is a substitution effect. Is that charge? Charge, substitution. Are those the same words? No. Is it size? No. Electronegativity? No. What the hell? Where is it? Where's the substitution effect in that list? Induction? No. It's the O-carp moment. Okay?
Hybridization.
It isn't quite hybridization. It's right after hybridization. It's a substitution effect. Okay? So it is one of the last things that we could be looking at. It is ultimately an atom effect, okay, or kind of a cross hybrid of atom versus molecular effects. Okay? But it is there. We do need to be considering it when we think about stabilities. Okay? And something had flashed while I was talking about that. Oh, the names of those things. Why do we call the bottom one tertiary? Okay. The official rule, and I don't necessarily agree with the party line, but this is the party line, an atom bonded to 3 carbons is tertiary. An atom bonded to 2 carbons is primary. No carbons? Officially, the party line is not zeroary. It's methyl. Nobody likes the word zeroary. I think we should just bring it in. So, future classes, be sure to reference it as zeroary and see if you can get some traction on that. They might laugh at you, though, just so you know.
The actual Latin or Greek that primary, secondary, and tertiary come from to find something a little bit less tolerable?
No, there's nothing wrong with zeroary. Just enjoy it. Okay? So you'll sometimes hear it referenced as a methyl, cation, or anion. I try to refer to them as zeroary because it at least matches that pattern. Okay? I do tend to incorrectly say as long as it's not hydrogen, I don't care what's connected. If there's 3 things that aren't hydrogen, I call it tertiary. That's technically wrong. Right? The technicality of it is how many carbons there are. Okay? What if we had 4 carbons bonded? Quaternary. Would we ever have a quaternary carbocation?
No.
Why not?
Because it's 4. Like it does not have a charge. It's 4.
If there's 4 things bonded to it, we can't have a carbocation. We also couldn't have the carbanion because we would have exceeded the octet. Okay? So that's why quaternary doesn't show up on our ion stabilities, but we can have quaternary carbons. Okay. Zwitter ions. I think the literal German translation is twin ions. So when you're looking at a compound, this middle one is known as a Zwitter ion. Why? It has the positive and its twin, the negative. So if you have a structure with both a positive and a negative in that same structure, it can be referred to as a Zwitter ion. Right? Where this is coming up is super important because what this is referencing is an interesting molecule. What is that molecule? Dang, Mike, and those hard questions. So let's look at the left-hand side of that molecule. What functional group is that? An amine. And an acid. So if we put that together, it's an amino acid. Okay? This is the fundamental building block of all of our proteins. Okay, we're looking at amino acids. These become important functional groups to evaluate because what can you tell me about amine chemistry? Well, amines have a lone pair. What could that lone pair potentially do? Resonance is a theoretical option with a lone pair. In this case, there's no resonance for that nitrogen for this structure. It could share with a hydrogen, which means the amine is acting as a base. What does the acid act as? As an acid, yes. Okay, and we could donate that hydrogen by collecting the electrons back, and we can end up with that. So what we're looking at here with an amino acid is a tricky functional group because it has both base chemistry and acid chemistry in the exact same compound. Okay, this wouldn't necessarily be an issue until we say maybe dropped this species into a water-soluble environment. Like your blood. It's all water-soluble. So you mean literally the entire time we deal with amino acids, we have to worry about this acid-base characteristic? Yes. Yep, all the time. Which means what you end up being responsible for in biochemistry is saying, okay, if I'm at a low pH, so now that water environment has lots and lots of protons floating around, what happens to the structure? Right? If I'm at a neutral pH, what happens to the structure? If I'm at a basic pH, what happens to the structure? Would that change how it interacts with the environment? We're starting with something, in the case of an amine, if we look at the high pH, neutral, becoming charged. Right? Are we going to see a different interaction? Yeah, a charged species is going to get me an ionic interaction. That's a much stronger attractive force than, say, if I was in the neutral state and I have hydrogen bonding. Remember all those intermolecular forces from the first unit? Yeah, those are dictated largely by these charges. So this is why when we think about biological systems, what pH do they tend to exist at? Neutral. All things exist at neutral pHs? No. So if we think about all living things that we know to date, what can we describe about every single one of them? They all function at constant pHs. All of our living cells have very narrow pH ranges in which they exist. We can find organisms that exist at very low pHs, high acidic environments. But if we take those organisms and move them into a neutral system, what happens? They die. Why? They've built a system based off of intermolecular forces within their protein structure. Okay? At that pH. You change the pH, what happens to all the intermolecular forces? They all change, which means the system that they expected to be a strong interaction now becomes weak. Okay? That's kind of a big deal. Like if you were rock climbing and you've got the ropes that you expect to be a strong interaction, but all of a sudden they become weak. That's kind of like life and death. Same thing happens with our biological systems. So they all exist in a very narrow pH, and they've built systems around that pH. That if you vary outside of it, it's doing it for a reason that they can bring it back to. Okay? That allows us to get that functionality behind it. But that also means is us studying those things, we have to know what those structural changes are. Which means we get to go back to a very famous equation, the Henderson-Hasselbalch equation, and use that to predict something about the charge state. Is it charged? Is it neutral? Okay? And that is our Henderson-Hasselbalch, or Hasselhoff, depending on who you talk to, equation. Okay? So how could we use that to predict the charge state for this molecule? All right, let's pick a pH.
7.
That's boring. Sorry.
Ouch.
1.5. What is the charge state for this molecule? Okay. So we're looking at, there was a good question. We're trying to figure out which state. Is it A minus or HA? And really all this is saying is the conjugate base and the conjugate acid. Okay, so to do this, we would need to know the pKa's. So when we go up and look up this, you'll find the pKa of that acid comes in at a 2. For those of you wondering, well, didn't we say that was 4? At least Christian did, so he should be wondering. Why is it not 4? Why did it drop to a 2? Because of the groups attached to it. You mean like this electronegative nitrogen, through an inductive effect, is now making that slightly more acidic? Yes, exactly that reason. Okay, so the pK of the side chain, the acid part drops significantly due to an inductive effect. The pK is about 2. So we look at our comparison, we could go through and solve this, right? pH, we said, was 1.5 equals 2 plus log. We had the base over the acid. Okay, we do all the math. We get negative. I can't do the math. This is why I don't teach that class. 0.5 equals log of the base over the acid. And then the base over the acid equals 10 to the negative 0.5. What does that mean about the concentration of the base in the acid? Exactly. That stuff is not hard to process. Other way around. That stuff is hard to process. Okay, and we'd have to deal with that manipulation. We're looking at a number less than 1. For the number to be less than 1, what does that mean about the relationship between the base and the acid?
There's more acid than base.
There's more acid than base. So at a pH of 5, what happens to the carboxylic acid functional group? Should it have the hydrogen on or off?
On.
Should have the hydrogen on. Because we're in an environment that is more acidic than the pKa. Okay? That's a lot of mathematical work and mumbo-jumbo that we have to go through and solve. This is why somebody went through and just said, well, let's just look. If the pH is less than the pKa, then keep the proton. Make it HA. What does it mean if the pH is greater than the pKa?
Then it's just A minus.
Ditch the proton. If you've got that system, you're set and locked and loaded. Okay? Now it's a relatively straightforward, simple solve. All I have to do is memorize this system, not memorize Henderson-Hasselbalch, not memorize it. I have to do mathematics and all that fun nastiness. Like, that's just a lot of work. Okay? Some of you are laughing. Hopefully you're laughing because you agree with me and not the fact that you think I'm an idiot that I don't want to memorize any of that. Okay? But that then sets that up and solves it all for you nice and neatly in one succinct package. Let's drop in the last little bit that messes with this. Okay? According to that analysis, what should the charge be on our structure? So we just evaluated this part of it, right? Should the hydrogen be on the structure or off the structure? What charge is that functional group now?
Neutral.
It's neutral. So what's the charge of the molecule?
Positive.
Did I answer the question about the other functional group? Nope. So what do I have to do?
Answer the question.
I have to answer the question about the other functional group. So when asking for this charge state, I actually have to do 2 calculations, 2 comparisons. For those of you who I'm just going to do the Henderson-Hasselbalch. That's cool for you. You now got to do 2 times the amount of mathematical stuff. Okay? You won't ever have a calculator with you again. That's a lie. But okay? So let's go through and take a look at the nitrogen. What is the pKa for the nitrogen? 9 to 10. So if we're at a pH of 1.5, what should happen to the nitrogen? Should it be A minus or HA?
Oh, oops.
It should be HA. The pH is less than the pKa. I should have the hydrogen on. This is why it becomes tricky for the nitrogen. If I have the hydrogen on, is it HA? No, it's HA plus.
Yeah.
Why has it become trickier for the nitrogen? Because the nitrogen acted as a base. So when you move into biochemistry, that becomes the tricky question. You have to deal with and know the protonation states for each of your functional groups. Okay, for the amine, NH2 is the neutral state. The protonated state is NH3 plus. It's not as straightforward as HA and A minus. Kind of, sort of? Okay. What makes this really exciting? Has anybody taken any biochemistry yet? Or biology classes? Cool. We got a couple people, so that should work. What is the structure for serine? There was a reason I asked if anybody has taken a biochemistry class. Seriously, none of you. You got like 5 people raising their hands. You can't tell me the structure of serine.
No, we didn't have to memorize it.
Fudge. I haven't taught the class in too long. I think I'm going to draw cysteine. I can't.
C3H7 and O3.
C3H7.
Yeah, they.
Fudge. I don't remember.
It's a CH2OH. So it's not all with. Yeah, so that's another. Yeah, there you go.
Cool. So we could go through and draw out a protein, an amino acid. What's E? E is one of them. Let's just draw in some other stuff. Okay. So we could draw out a structure for multiple amino acids, okay, that get a chemical linkage between them, and we could evaluate that protein sequence all the way through. Okay, that's a lot of writing, right? Do biologists like writing chemical structures? No, so what do they do instead? Okay, they come up with codes. They use 3-letter codes and they use 1-letter codes. So we get the 1-letter code for serine, S. Because it's biochemistry, I'm allowed to do this. What we have here is literally a protein sequence. What you could be asked for is, what is the charge on this protein?
That's some scary shit.
You would have to be able to interpret out, and for those of you moving into biochemistry, welcome to life in next semester. Okay? You will be asked to take that protein sequence, code that information out to what the structures mean, to know what the side chains are. Because the side chains could be acid-base reactive, which means instead of just being the amino and the acid that you're dealing with for charge, you also have to deal with the side chains. And you would have to go through and decide what is the charge on the overall protein. Okay? To do that, you have to know what each of the individual 1-letter codes are. So you have to be able to first do the biochemistry to then be able to get out to do ultimately organic chemistry. Okay? It is actually kind of interesting. It's fun. See that effect? No one likes solving for it, but that's cool.
I figured out what E was.
Glutamic acid. Yeah, I think I changed it around to bring E in because I needed that. So we're now done with chapter 6, which takes us into chapter 7. So one of the things that Carty brings in that I agree with, but I think it's a little bit difficult to kind of wrap your brain around, is this idea versus electron-rich and electron-poor. Electron-rich species are electron donors. They tend to be negatively charged. They're Lewis bases, Bronsted bases, nucleophiles. They typically have high electronegativities. Okay? you're also typically looking for species that are nonmetals to metals. Okay? For instance, if I drew out the compound, do I have an electron-rich compound in NaCl? So electron don't. It's not negatively charged. Since it's not showing a reaction, I can't actually call it a Lewis base, Bronsted base, or nucleophile. Okay? High electronegativity, yes, chlorine has a relatively high electronegativity. We are hiding the electron-rich atom. Where are we hiding the electron-rich atom behind?
The sodium.
The sodium. That's our metal. Okay, in that classification. I totally miscolor-coded that. So if we erase the sodium because it's a spectator ion, what do we now have? Chloride, negatively charged. That chloride can share electrons. It's an electron donor. Because it's an electron donor, it could be a Lewis base and a nucleophile. Why can't it be a Bronsted base? If it acts as a Bronsted base, what does it form? HCl, and HCl is a strong acid. And strong acids, by definition, completely dissociate back to the chloride, which means it's not acting as a base. Okay? The electron poor, similar idea, just the flip of it. These tend to be electron acceptors, positively charged, Lewis acids, Bronsted acids, and electrophiles, typically lower in electronegativity. And then your electron poor are nonmetals to more electronegative nonmetals. Okay? So in the previous case, could I call sodium chloride, could I call the sodium an electron poor? It's positively charged, but it doesn't really qualify as the electron poor atom. Okay? And yes, that is tricky to deal with, and that's largely because sodium is a spectator ion. So when we're looking at electron pores, carbon bonded to hydrogen. Well, that's nonmetal to nonmetal. Does that mean I have an electron poor atom in the hydrogen or the carbon?
No.
No, it does not. Why? What is the difference in electronegativity between carbon and hydrogen?
Low.
Very, very low. So we aren't getting a large difference, which means we don't generate a large positive charge. What happens if I, however, bond that carbon to, say, chloride? Okay.
Now you get electron. High delta.
Now I have a large difference in the electronegativity. I could reference that carbon as being partially positive. At that same time, though, what could I reference the chloride as being? Partially negative. Is this species electron rich or electron poor? It's electron poor. For it to be electron rich, what would have to happen? Chloride would have to share electrons out, which means chloride then has 2 bonds. Is chloride allowed 2 bonds?
Yeah.
Not happy with 2 bonds minimally, so that is not an electron-rich species. What is that chloride doing? Stealing electrons from the carbon, making the carbon electron poor. Once the chloride has left, we now have Cl-, and Cl- can now be classified as electron-rich. But it has to have left the structure first. Okay? Kind of makes sense? Okay. So those are our big differences on electron poor versus electron rich. We will see those fairly often pop up all over the place. The other thing that pops up in Chapter 7 is another intermediate. Okay, Chapter 7 made reference to the carbocation intermediate, and we saw that with rearrangements, okay, which will haunt you and give you nightmares. The other one that will also give you nightmares will be this one. Okay? This intermediate is known as the ketoenol intermediate. Okay? So it's just an interesting structure to draw out. If we go through and draw this compound, you should note that there's a resonance structure, right? That negative oxygen could share electrons with the carbon down below, which then shuttles electrons to that carbon. Right? That then generates this other structure where the negative charge is on the carbon versus on the oxygen. Okay? Because we have 2 negative charges and different negative charges, what do we have?
Two basic sites.
There are two basic sites, which means when this reaction runs, when I now mix it with an acid, shown in the middle, I could end up with two possible products. I could end up with the product with the OH, and I could end up with the product with the, CH. Right? Do I need to draw in the rest of the bonds and atoms?
No.
No. Okay? So the question becomes, which of these is the dominant answer? Okay? Or do we get both? Okay? Because both is always a possibility.
I would guess that would be tilted towards the OH.
Okay? So why do you think the OH should form?
I think you would get both, but you would get more OH than you would get
So
CH.
why do you think we should get more OH?
OH is, the O is going to be more negative. I think it's going to be a larger resonance contributor. So it'll spend more time in that form than it will in the other ones because the negative charge is more comfortable on oxygen than carbon.
Does everybody track that? He's saying if we look at these two form resonance structures, we'd rather have a negative oxygen than a negative carbon. So your argument is the negative oxygen is the best resonance structure.
It's a less bad resonance structure. It's just
Then what?
more
Less bad than what?
Than
this?
yes.
Okay. I'll accept that. If we look at this compound, though, there are two resonance contributors. We have one and we have two. Which one is the best of those options?
The top one.
The top one. When we talked about resonance, I made a very peculiar reference to it. And I said one of the resonance things that you should be considering and always looking for is not necessarily the best. You should be looking at the least worst. Okay? Or the first worst. Best, worst, some possible combination thereof.
I changed my answer.
Okay? And if we use that analysis, we would say the other form comes in dominant. Okay? Well, what happens? Sorry.
Comfortable being that phenol form.
The end result is that we very heavily favor the acid-base reaction happening at the negative carbon, not at the negative oxygen. One analysis that you could use for this, which one's more reactive? Negative oxygen or negative carbon? Negative carbon. So yes, the oxygen is there. It may be there in the largest amount, but it is also not likely to react. Okay? So we could use that as an analysis behind why we would expect the carbon to pick it up. Another reason that we could potentially pull off, if we go through and compare the oxygens in our final product, okay, which oxygen has more electrons around it? And yes, that could be a trick question. It's not. Which oxygen do you think has more electrons around it?
The one on top.
Okay. The one on top is a suggestion. They both have two lone pairs, yes?
Yes.
So let's wipe that from the record. Okay. They both have a bond to a carbon. So let's wipe that. We're looking at a bond to a hydrogen or a bond, second bond to a carbon. That second bond to a carbon is a pi bond, which does what to the distance between the oxygen and the carbon? Shortens them, which means those electrons are now closer to the oxygen than they were in the top case, which would suggest the bottom one actually has more electrons around it than the top. Does oxygen want more electrons around it?
Yes.
Yes, because it's more electronegative. Ultimately, one of the biggest things that I want to get out of this is these are really hand-wavy arguments that we're using after we know the answer. Okay? Officially, how do we know this to be true? Experiment. We test it, there it is. Okay? Now it's up to us to try and come up with an explanation behind it. That difference is very, very subtle. Okay? And you can go all the way back through and look at bond energies to define that the enol or the keto form is better than the enol form. Okay? That very subtle difference is enough that we only see the keto form. We see very limited amounts of the enol. This means that if running through a reaction we form an enol, what should we immediately do? Not go back and try again. What's the enol going to do? Turn into the keto form. Okay? It will self-convert from the enol to the keto form. This is known as the ketoenol tautomer. Okay? Keto taking precedence, so it's already in the name. It's not enol to keto, it's ketoenol because the keto is our primary structure. That's the most important one. So if you see something show up where you have the pi bond and the alcohol, that is known as an enol. Why is it not an alkene and an alcohol? What functional group is that? Carbonyl. What functional group is that? What functional group is that? It's not a carbonyl and an alcohol? No, now it's a carboxylic acid. Why? You've connected them, the functional groups affect each other, it changes their chemistry, so it changes their name. When we put an alkene and alcohol in close proximity to each other, what happens? It changes the energy of the bond. The whole system changes. We get a new functional group. That functional group is known as an enol that very quickly converts into the keto form. Right? That's the bottom line you need out of it. However you want to deal with memorizing that, that's cool. Right? We will see that result come back and bite us in the 4th unit. Okay? That's going to show up with our addition reactions. Okay? So, we all saw this before. So let's take chapter 6, 7, and a little bit of 8 here and put them all together into one giant thing. Okay? So we've done curved arrows, yes? You guys were confident in your ability to do those curved arrows? Indeed. So you can walk me through those without any problems?
Correct.
Okay, Dave, you can give me one. Everybody else? You're the only one that said yes, so that's why I was checking. Everybody else confident?
Yeah.
Okay, David, give me the first one.
All right, you draw a line from the one of the lone pairs on the oxygen to the hydrogen, and then you draw a double-headed arrow. No, all the way left. There you go.
I like a little bit of condensation in there too. That was nice. It was a good touch.
I am pleased.
All right. What happens in the next step? What do you got, Eden?
The oxygen takes electrons from the carbon.
Why would the oxygen take electrons from the carbon?
To neutralize its charge.
Oxygen doesn't want to be positively charged, so it steals electrons. Why did you pick them from the carbon and not the hydrogen?
That's a common.
You're probably making it harder than you need to.
Yeah.
What's the next picture show?
It broken up.
The carbon's the one missing the electrons in the next step. So that's why you picked from the carbon. Okay? We don't have to make it that hard.
Okay.
Okay? To make it harder, we could go through and say if we removed one of the hydrogens, all we do is go backwards, and then we undid David's work. And while that could be fun, let's try and do something a little bit different. Okay? So we end up with the next result. No one wants to volunteer the next one.
I will.
The hydrogen takes the electron from the carbon underneath it, breaks off, giving that one the positive. Yes.
Okay? What's your problem with that?
For that to happen, that can't just break off on its own. Something would have, and there's nothing there. So the hydrogen wouldn't break off. The hydrogen would move, the carbocation would shift, because that carbocation is secondary, and we want to make it stable, so there's a tertiary condition present.
That was a lot. Let's see if I can pull some of that back. So your argument out of the gate is that the arrow that we've got drawn there is a bad arrow, that it can't happen. Why can't it happen?
Protons can exist alone.
Protons can sort of exist alone. It depends on who you talk to and what timing. It's not sort of, and ultimately, the reason why I'm being kind of dismissive on that is it's not a proton.
That's hydride.
It's hydride. It's a hydrogen with an electron. Why would I expect hydrogen with an electron to not just come off on its own?
Because hydrogen is less electronegative than carbon.
It is charged. What is its size?
It's really
Very
small.
small.
Hydrogen is the smallest element. Can it stabilize that negative charge?
No.
No. Does it have a decent electronegativity, maybe?
No.
No. Does it have any resonance? No. Does that? There's literally nothing that supports that negative hydrogen. That is incredibly unstable, and so it cannot just come floating off on its own. Okay? But Felicia does have a point. That hydrogen needs to leave that position because we see the positive charge forming there. Okay? But what she didn't see was what happened to the old carbon where the positive charge was.
There's a hydrogen there.
It's now neutral. For it to be neutral, it has to have a full octet. If it had a full octet, it wouldn't have been charged here. How did it get its full octet? That hydrogen, if we want to think about it this way, could come off. Oh, we're not allowed to show that hydrogen come off. Okay? So it had to come right back on. Okay? But I can't show the hydride existing on its own because that's bad. So I have to combine both of those arrows into one fell swoop. And I end up with that, which can be confusing.
Why did you do
Okay?
that?
Which can be confusing. So what we try to do is throw a little curlicue in there to help emphasize the fact that we're doing something a little bit odd. This is a shift of an atom. This is a hydride shift. Okay? What happens in the next step? Okay.
The electrons from the bromine attach to that carbon with the positive charge, making it neutral.
Okay. And I screw this up all the time, but I'm trying to work on it. Is it bromine?
Bromide.
It's bromide. Okay, you should be referencing it as bromide to be fully correct because we will work with bromine. Those are two drastically different molecules. Bromide is a nucleophile. Guess what bromine is? It's an electrophile. So we have to be very careful to differentiate those, and it's not an easy one to nail down. Right? So the type of mechanistic steps in the first one, acid-base. And the next one, heterolysis. And the next one, we have a rearrangement. That just says a rearrangement. And the last one is coordination. I don't know if I asked this one, but we're going to ask it now. What type of reaction happened beginning to end?
You put an alcohol and mixed it in with hydrochloric acid. The reaction of alcohol.
So I've heard an E, which would be elimination. Eliminations
No.
form pi bonds. Did I form a pi bond? No, it is not an elimination.
Substitution?
Okay? Is it a substitution? Do I have a leaving group leave?
Yes. No.
Did something leave the original structure?
Yes.
Yes. Okay? Did I have a nucleophile attached to the structure? Something new come on?
Yes.
Yes. Guess what kind of reaction this is?
Substitution.
Substitution. Okay? For those of you shouting out SN1 or SN2, that's not the question I asked. The question I asked was what type of reaction. Okay? Mechanism is a different system. Okay? And an SN2 mechanism says it all happens at once. Did that all happen at once? Nope. This is multiple steps, so it can't be called an SN2. Okay? So, energy diagram. This becomes an interesting one right out of the gate. Okay, and we'll address both components behind it. We'll just start with my first reactant, somewhere in the middle. Why pick the middle?
Because we're going to have to go up and down.
I could go up from there or I could go down from there. Since I don't know necessarily yet, I'm just going to pick right in the middle. Okay? My first product, should that be higher or lower?
Higher.
Why do you want to put it higher? Okay, that structure is charged, so we might expect that intermediate to be higher. Okay, how about the next one?
Lower.
Why should it be lower?
Lower than the second one, but not as low.
Why lower than the second one?
Because
Not you. It's okay.
Isn't the positive more comfortable in carbon?
Why would we say the positive is more comfortable in the carbon than on the oxygen?
Because oxygen more electronegative.
Use our ranking systems. Charge, they're both charged. Size, carbon versus oxygen. Electronegativity. Oxygen would rather have its electrons. So that makes that carbocation a little bit lower in energy. Yeah? Okay, how about the next carbocation?
Also slightly lower.
Okay, now somebody else. Why do you agree or disagree with David? What makes both of those structures unstable? Charge. What charge? A positive charge. Okay, no, and that positive charge located on what atom? Carbon, so we could call it a carbocation. How many carbons are connected to this carbocation? 2, which would make it secondary. How many carbons connect to this carbocation? 3, which would make it? Which one's more stable? The tertiary is more stable than the secondary carbocation. As a positive charge, it is unstable because it's missing electrons. The tertiary brings in more electrons. Okay, so that can stabilize it a little bit better. That should drop in energy again. Okay. Last one. Lower than what? That very last product with the bromine on it. Should it be lower than this carbocation? Why? It's neutral. It's not charged. Yes, it should absolutely be lower. Should it be lower than our starting material?
yes.
Why? That's a pretty hard one.
Because the reaction happened.
Technically, we don't know that.
Is it because it's bigger?
Okay. That placement on that product, I'm not that concerned about. As long as you place it at the reactant energy or lower, I'm okay with it. We could go through and say lower because we're assuming the reaction happened. That is an assumption we're putting into it. Okay. One of the things that's going to factor into that happens to do with some of the reversibility of those reactions. Those are subtle nuances that I don't really care about. As long as you place the product at the level of the reactant or lower, I'm okay. If it goes higher, what am I going to expect?
A reaction doesn't happen. Or
An explanation. Right? If you're going to place your product higher in energy than the reactant, you better have an explanation for why you're doing that. As long as you've got an explanation that gives me some logical reason to be like, yes, I can accept that, then you're good. If you don't, then we got a problem. Okay? So if we draw this all together, you're like, doesn't that look ugly? Yes, I don't care. We've got the general idea behind it. I'm fine with it. Which of those steps would you expect to be the slowest? Probably the first one. Why? Highest activation barrier. Turns out it's not the first one. It's the second one. That first reaction is what kind of reaction? Acid-base. What do you know about acid-base reactions? They happen readily. When you add acid to water, is it acid to water or water to acid? Serious? Gen Chem? Oh, well, it's my fault too. We should have talked about it in lab already.
Can't remember acid to water.
Acid to water. Why? What happens if you do it the other way? In theory, it boils and it spits concentrated acids everywhere. Why? It's an acid-base reaction. all acid-base reactions are exothermic. Is that really what we just drew?
No.
Yeah? Reactants to products, is that an exothermic reaction?
That's an endothermic.
No, that is heavily drawn as endothermic. Okay, I'm fine with your analysis on that. Okay, perfectly acceptable. But realize it is not true, and the reason it is not true, and this is what I find irritating, is that when we look at it, it's actually this. Okay, why do we have that big drop there? The reactant energy, when we went through and evaluated, what did we look at? The carbon structure. Okay, why is that important? If you evaluate the carbon structure, you'll probably get the drawing we drew in black. If we actually factor in the other species, that can mess with our energy diagram. How stable is H+?
No, it's
Not very stable at all. Is it more stable here?
yeah.
Yes, because octets.
It's
Okay. If you factor in octets behind your Lewis structures, you see a massive drop in your acid-base reaction. The slow step is actually the leaving group leaving. Okay? Just want you to be aware of that. Okay? When it comes to a test, what I would do is ask you to explain why you're placing those things. As long as your explanation is solid, I'm good with it. Okay? And we just walked through 2 explanations for that. Make sense? Okay. Will you be expected to draw an energy diagram? Absolutely. Okay. Which gets us into our next section, pretty much chapters 8, 9, and the rest of the semester. What we're now looking at is 5 major reaction classes. Chapter 6 was acid-base. All we do is transfer a hydrogen. Chapter 8 and 9, Cardi kind of mushed together, and I don't disagree with his analysis. I also don't agree with it. Okay, so he kind of smushed 8 and 9 together, said these are substitution, these are elimination reactions. Get used to kind of the pieces behind them. Chapter 9 is now that you know what substitution elimination reactions are, how do you know it is substitution versus elimination? What are the pieces you have to evaluate behind each of those? Okay? If you remember when we got back from spring break, I said there were 4 videos that you should go home and watch, okay, about substrate, nucleophile base, leaving group, and solvent. Those are the 4 primary characteristics found within a substitution and elimination reaction. Okay? So if you know what those pieces are, you can then start to evaluate those pieces and decide, oh, when I ran a SN2 reaction, I saw that the nucleophile was negatively charged. A negatively charged nucleophile would also happen to be a strong nucleophile. So now I can start making the guess that the next time I see a negatively charged nucleophile, it's going to run SN2. Okay? And I can start to draw those conclusions. We started today's lecture off with 10 review slides. If you go in and look at those 10 review slides, you will see those exact references. Each of those categories is broken down by preference for each of those mechanistic types. Okay? What we're effectively spending the rest of the next 4 lectures? God, I hope it's 4. I sure hope it's 4 lectures. Next week isn't April 5th, right?
No. Yeah, next Friday.
So I get 1, 2, 3, I get 4 lectures before the next exam, if we don't count today. What we're going to be doing is spending our time looking at substitution elimination reactions, identifying those pieces and saying that piece means this type of reaction happens. So you need to be able to look at these general formats and be able to tie them out. For the addition and the radical, you don't got to worry about those yet. We'll look at both of those reactions in the next unit. Okay? What I do expect you to be able to do with the addition and the radical, though, is to be able to tell that that was an addition reaction. If I give you an addition reaction on the test, I want you to be able to look at it and be like, jerk, I don't need to know anything about that except that it's addition. Okay? That's what I want you to be able to do. How could you do that? You could look at this convenient, handy-dandy slide that summarizes the results. And in addition reaction, what do we start with? pi bond. Do we start with a pi bond in an elimination? How about a substitution? How about in an acid base? No. Okay, which means if I see a pi bond, addition. Yeah, manchia. Shh. Look at the substitution reaction again. Do you see a pi bond? Yes. So does that mean it's an addition now?
Because it doesn't change.
Right? When we're looking at these reactions, it's not just, oh, there is something, so it's that. It's, does it change through the course of the reaction? In the addition, what happened to the pi bond? It disappears. Disappears is a horrible term. Good reference. It became 2 sigmas. Okay? If we go through and look at what I did up here, there's the pi bond. What happened to the pi bond in the course of the reaction? Nothing, which means it has no bearing on that type of reaction. I'm going to be more concerned about what does change. Okay? This is huge. Okay? Students will move from exam or lecture time to exam and be like, well, I haven't seen any of those structures before. You don't have to see any of the structures before. I could draw a purple elephant with a substitution reaction off the nose of it. Okay? As long as the reaction's happening out there, what do you draw? Purple elephant with a little thing happen off the end of it. I don't care about the elephant as long as it's not doing anything. Okay? But that does mean I do need to draw it through the whole process. It sounds kind of like a fun question. I might have to write a question like that. I'll teach you how to draw pineapples, don't worry. Okay? So, recognize these classes. These are our major reaction classes. What happens in second semester? Well, I'll do an addition with an elimination. We go, oh my God, it's a new reaction. No, it's the same friggin' thing you did up here. It's just an elimination and an addition. In fact, what do we call it? An elimination addition reaction. Seriously? Yeah. And yet everybody thinks it's a new thing. It's the exact same thing that we've already been doing. All you're doing is stacking these pieces. Okay? So, this is another one of those big summary slides. Okay? So let's draw attention to some of these, the titles, and we'll go back to our general reactions. We get substrate, nucleophile, solvent. Okay? You'll notice one thing is missing off of this list that you should be sort of maybe passingly familiar with. What 2 words are left that aren't mentioned on this slide? No. Begins with an L. Leaving group. The leaving group has disappeared from it. Okay? Why has the leaving group disappeared from my summary? Because it leaves. As long as it's a good leaving group, it leaves. Okay? If it leaves, do I do a substitution? Yes. If it leaves, do I do an elimination? Yes. Do I care about a leaving group? No, it doesn't really have any bearing on the reaction, okay, as a substitution or elimination. It could have a bearing on this reaction does not happen because it doesn't have a good leaving group, okay? So you do have to evaluate it, but it's not going to dictate which reaction you're doing, okay? So let's go back to these. Which of those symbols do you think is leaving group? LG. Super creative and purple. So there we go. Here's our key. Leaving group. Okay, what do you think NUC stands for? We have a nucleophile. Nucleo. There we go. Notice in red I also have base. What do you think base stands for? Yeah, base. Why are they both in red? What does a base do? Accept a hydrogen. How does it accept a hydrogen? By sharing electrons. What does a nucleophile do? Shares electrons. Right out of the gate, we should be seeing some confusion between these 2 reactions. I'm using a single species, and that single species, depending on the reaction, could act as a nucleophile or a base. Would that change the products I get out? Yes. Okay. So we need to come up with some way to distinguish those 2 things from each other. Okay. This is kind of a dumb one, but I'm going to say it anyway. What's the solvent stand for? Solvent. Where's the solvent typically written? Typically under the arrow. Okay? There's a psi and a typically there because it's not always the truth. Okay? So be careful with the solvent. Sometimes the solvent can form two roles. The solvent could also act as a nucleophile. It could also act as a base. So solvents are very dodgy to deal with. Take that into consideration. So what's the last piece? I mean, I had it flashed up there for like a good 30 seconds. You should be able to tell me all the names that were listed on that next slide. Nope. I don't have an electrophile written up there. Substrate. It's the thing I'm reacting. What am I starting with? Okay. So I'm taking a nucleophile, reacting it with a substrate. Notice I don't look at the product. Okay. Products have a very limited effect in our overall reaction. Why would they have a limited effect? No ideas?
Once you make your product, it's done.
It's kind of already happened. We've kind of.
The reaction is no longer.
So they tend to have a very minimal effect because we have to get to being a product first. How do we get to being a product? We move through the activation barrier, right? Which means our reactants must react to get over there. Okay, so the products make a relatively minimal impact on our result. That said, the elimination products can dictate where your reaction goes. Okay, so we do have to watch those a little bit, but the products play a relatively minor role when we're looking at discussing these reactions. Okay, so again, our big summary for SN1, SN2, these are all of our big summaries for both substitution and elimination. Okay, we're going to look at each of those details here in a second. The next big thing that I want you to be aware of is complications. Within each of these mechanisms, there are things that can compete, that can change the reaction and can shift where we're going. Okay? A big one in substitution, SN1 and E1. The second one on SN1 says, maybe third one, depending on how you want to look at it, simultaneous E1. If I think I'm running an E1 or an SN1 reaction, what's probably also going to happen? An E1 reaction. Why might that be the case? Because the basic patterns behind why an SN1 reaction happens are the exact same for why an E1 reaction happens. So if I now asked you to do a reaction, I want you to do a substitution reaction, is an SN1 a good choice? Why not? Because I would also do an E1, which means what happens to your product yield? It goes down. So when we think about the synthetic usefulness of each of these mechanisms, the SN1 and the E1 tend to be relatively low on that scale. Because they compete with each other, we get multiple products. That limits our yield. So when we think about synthesis, SN2 and E2 tend to be the more popular categories. That said, I think the SN1 and E1 are easier to manipulate and talk about. Okay? So let's do a quick breakdown of what we see in this substitution reaction. So what bonds were broken? What bonds were made? So we broke the carbon-iodine bond and we made the carbon-chlorine bond. Okay? So two things have happened in the course of this reaction. That is it, only two things. What are the possible ways that we could put these two things together? Not even with arrows. Okay, as a hint, I could break the carbon-iodine bond, then I could make the carbon-chlorine bond. What else could I do?
Make the carbon-chlorine bond, then break the carbon-iodine bond.
What else?
They happen at the same time.
So there are 3 possible ways to do a substitution reaction. Okay? We've just talked about substitution reactions and the possible ways you can do them. There were 2 different types, right? One of these is impossible. We'll start there on Wednesday.